excited to be in IJS this year in London, and welcome to my session. And today we are going to understand how a lot of the mechanism in Node.js platform works, how the event loop works, how the memory management mechanism works, and it's going to be challenging but fun. But before we're gonna start diving into those really heavy stuff, I would talk a little bit about myself because it's an obligation. And the clicker is not working. Okay, it is working. So, my name is Tamar. I'm a software engineer. I manage large development teams. I'm a software architect. And currently, I'm an architect in Palo Alto Networks, in a group which develops in Node.js. Palo Alto Networks is the largest cybersecurity company in the world right now. I was a CTO of a startup of my own. It was social networks for food lovers, and I'm extremely passionate about Node.js. I'm working in that technology for several years, and my big interest in that technology started when I wrote the entire backend of my startup in Node. And you can all follow me on Twitter. That's my Twitter handle in bold in the bottom of the screen. And all of the material, all of the demos would be available there in, I think, 2 hours from now. Other things that I want to say about myself, that currently I'm on maternity leave. I have a son who is 5 months old. And this is a picture of my son, very cute. I have 3 kids. I'm also a professional violin player. And I'm a technical community leader in the JavaScript Israel community. We have several lines of meetups, and we present a lot of advanced topics in JavaScript. And so when you're in Israel, come to one of our meetups. It's very cool. So now, after talking about myself, let's start with the thing that you want to hear about today. And let's start with an introduction. I would like to speak about the traditional approach of languages like Java, like C#, like Python. So in those languages, the approach or the perception that is used is blocking I/O, meaning that when I am doing an I/O operation, I am doing a database query right now. I am sending an HTTP request, so my thread is waiting for the results. And this is actually making a lot of sense, because usually when I am doing a database query, I want to do something with those results. I mean, I want to parse them, I want to process them, I want to do something with that. It's like combining very well with my flow. So what's happening in those systems is that usually each request is handled by a separate thread. So let's say that I have thousands of concurrent requests to my server. I would have thousands of threads handling those requests. And usually also, if I want to, let's say, execute a database query, I would usually open a background thread to execute it. And I would want to think with you, what are the problems with this approach? So first of all, we have a lot of threads. A thread is not coming for free. It has an overhead of a CPU, of memory resources. It has other overheads of, like context switching. The system is actually doing context switching between threads. So when the system is stressed up, so a lot of resources, or your hardware resources, are being wasted on context switching between threads instead of doing actual work. So that is the problem. That is the problem with those types of languages. And JavaScript itself was a non-blocking I/O from the beginning. when we're registering a callback, we're usually doing an asynchronous operation. And the entire Node.js architecture has come to support this non-blocking I/O approach. That means that once I'm doing an I/O operation, then instead of waiting for the results, I can just do other stuff. I can, do work which is related to other requests instead of just waiting. So let's go over the most updated architecture of Node.js. So we have an application here. Our application is built on the V8 engine. V8 is an engine to run JavaScript code very fast and was developed for Chrome. The binding of Node.js is bounded to, that square, which is presenting to us, that part is presenting to us the event loop and the worker thread pool. The event loop itself is here to support the non-blocking I/O concept, but we'll get into it really soon. But what is happening is that when a request is coming, their callback are being registered, and the event loop is starting. And the event loop is usually offloading I/O operations, asynchronous I/O operations, to the worker thread pool. Now, let's get into the details. So after we've spoke about the event loop and the worker thread pool, I guess that all of you heard a lot of time the phrase single-threaded with event loop. So the question is the platform really single-threaded if we have event loop and a thread pool? And the answer is no. Okay? The platform is not single-threaded because in the architecture diagram, we have several threads, okay? We have the event loop thread, okay? And we have the worker thread pool. So the event loop is running one thread, and the worker thread pool is a thread pool with a fixed capacity of threads, okay, that are doing I/O operations. So it's not single-threaded. Only the event loop itself is single-threaded, but the platform itself is not single-threaded. Now, if we're talking about the event loop thread itself, then, as I said, every request registered a callback to the event loop when it arrives to the server. That callback executes immediately, and then the other callbacks of that, request flow would just arrive to the event queue itself of the event loop. And if you're doing I/O operations as you should, asynchronously, then those I/O operations would be offloaded to the worker thread pool. Now, let's talk about the worker thread pool. So the worker thread pool is here to perform heavy operations. Just imagine that every heavy operation, usually this is I/O operations, and in most of the cases, there are some cases where when you offload to the worker thread pool, CPU-intensive operation. This is also something that you don't want that your event loop would do. You're offloading CPU-intensive operations. As I said, it's bounded by fixed capacity. It can be bounded by 10 threads or something like that. And it is based on an API called libuv. It's a library in C++. And that library is a cross-platform, works in all of the operation system, and that library enables you to submit an I/O operation in an asynchronous manner. Now, what I want to say that most of the modules in Node.js don't use the C++ libuv API. In most of the cases, you're using a set of basic modules that they are doing they're working with libuv directly. If you really want to be adventurous, you don't have to be so adventurous for that, but it could be a nice programming exercise to, submit a task to libuv API, and I recommend everybody to do it. But when you're writing an NPM package, you're usually not doing it. You're using some of those basic modules as FS, as DNS, as crypto, and those modules are working with libuv. But I really recommend you to do that. It's extremely cool. Now, I want to ask you a question, which is whether the worker thread pool is implemented with a queue. So we were talking about the worker thread pool, right? The worker thread pool is a thread pool for executing heavy operations such as I/O operations. So behind the scenes, this is actually, now the clicker is working. This is implemented with a queue. What's happening here that when an I/O operation is offloaded to the worker thread pool, then it enters into a queue, and that is the implementation, and all the threads over there are doing the queue and dequeuing the I/O operations and starting to execute them. Now, the question that I want to ask you is whether the event loop itself is implemented with a queue. Because it does make sense, right, that you have a queue behind the scenes and you push the task, the callbacks into the queue and everything, but the answer is no. So the event loop itself is not implemented with a queue. What's really happening in the implementation itself, that there is a monitoring of collection of file descriptors. Whoever doesn't know what is a file descriptor, this is an object of the operation system that can represent, let's say, a socket, that can represent a file. But what is happening here that the event loop itself is monitoring a lot of file descriptors, and when one of them is ready, it's getting a signal, and the execution callback of that specific heavy I/O operation is being inserted into the event loop itself. So it's not really a queue, it's more a popcorn. It's like whatever's ready is just, pops up and, gets into execution. Now let's talk about the event loop itself, because we are saying, okay, the event loop is executing a lot of callbacks, so it sounds like a complete chaos, because it's just like executing callbacks from all sorts of types. I mean, if I can work with Node.js, if I'm working with Node.js, I can think about timers, I can think about I/O, I can think about a lot of stuff. And why I want to tell you that it's not a chaos, okay? There is a very structured order of how those callbacks are being executed. Okay, so the event loop itself has several phases, okay, that repeating like forever, right? These are the names of the phases. We're starting with timers, then I/O callback, then idle prepare, which is internal, and I won't get into it in this presentation, then poll, then check, and then close. And the event loop itself is working in a while true, like a big while true, okay? And those phases just repeating themselves over and over again. We have timers, callback, poll, immediate, close. Then again, timers, callback, poll, immediate, etc., 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 forever. All right. So what are all of those phases? What is the the role of each one of those phases? So the timers phase is responsible for executing timer callbacks. Set timeout, set interval. Anyone in the crowd is not familiar with those functions? I need to explain what they're doing. Don't be shy. No. All right. So set timeout, set interval. So these callbacks are executed here. So if I have a set timeout, which is 5 seconds, it should happen in 5 seconds. So it would be happened in 5 seconds in the best case. It can happen after it. All right. So what I want to say also that this phase is not scheduling anything. It's just executing. Okay. It's executing all the already scheduled callbacks, all right? But there's no scheduling here. The phase which is actually scheduling is the poll phase. That phase is doing the scheduling and deciding what will be executed when. Now we're going to I/O callback phase, and actually it's not I/O callback, it's error, okay? Somebody have to talk to Node.js core team and tell them, guys, this name is kind of confusing because what's being executed in this phase, in the second phase of the event loop, is, for example, as I put in the code snippet here, error callbacks, like errors that are callbacks that are related to error events on socket object, for example. These are like system error callbacks, okay? That's what's happening here. This is not like regular I/O, okay? Then we are getting into the most important phase, the poll phase. That phase has a state machine inside, and it checks the following stuff, okay? It says first, whether I have timers that their threshold elapsed. And how it checks that? Remember, it's monitoring a collection of file descriptors, all right? So do I have that? If I do have, I'm going back to timers phase, okay? If I don't have any timers that, their threshold has elapsed, I am saying whether I have I/O callbacks to execute. Again, it's not a queue here. I wrote here poll queue is empty out of, maybe that you would understand it better. But behind the scenes, we're monitoring collection of file descriptors. I would say, okay, do I have some kind of a database query that has returned? Do I have an HTTP request that, I don't know, I got the response from it? Meaning if I have something, I am executing those requests, and if, the poll queue is empty, like I don't have any I/O operation to perform, I am continuing to check phase. Check phase, so that phase is doing scheduling and callback execution. It has two roles. So the check phase itself, now we will talk about the check phase and the close phase. So the check phase is executing callbacks that are related to set immediate, and close phase is handle like really fatal errors. Okay? Now I want to say something. I did not relate to process next tick here. I did not relate to it. Maybe someone know why? No. Okay, so when you're using process next tick, what would happen is that code would be executed immediately and the whole flow of the event loop itself would stop. Okay, so if you're using process next tick, okay, it's not in any of the phases in the event loop, and it would just cause your server to execute whatever process next tick is doing, and your server would be busy with that, and there is a chance that your server would be frozen. Okay? So, after talking about that, I want us to do small profiling to a little bit of code, some performance profiling. It's not going to be a deep profiling, but my purpose here is to explain to you how important it is to make all of your heavy operations asynchronous and always use asynchronous APIs. And the second goal here is to show you how you do performance profiling to your application that you would have a point to start from. Okay, so let's go into Visual Studio. And here I have two files. I'm using the crypto module. Okay, just imagine that this loop, by the way, is this size of the code is fine? Do I need to make it larger? It's okay. Okay, good. So, you can look at that code. What that code is doing a hash of a password, and there is a loop running here from 1 to 50. Okay, and then you have, what you're doing is generating a hash actually 50 times. You're generating that hash using the crypto API, and actually you're giving some kind of a salt, and you're using a crypto algorithm, SHA-512, if any one of you is familiar with. And okay, so, and then you're generating the hash. And here you're using the synchronous API. You see the word sync here, and here. In the second file, you're doing the same loop, but I am transferring a callback. All right, I'm transferring a callback here. Here I have another argument called callback. Okay, and this is an asynchronous version of this. And the asynchronous version will receive the callback. And the effect that we would have here is that that operation would go into the worker thread pool that I've spoke about so much. So after speaking about that, I would like to, I'm considering whether to open a terminal. Yeah, I would open a terminal, definitely. And I would see what's going here. I would just remove the file from the last run. And, sorry. Okay. Okay, so now I would run the code with some Node.js built-in flags that are meant for performance profiling. Let's do node syncrypto.js, but I'm going to use the flag --prof. When I'm using that flag, then my run would generate a report, a performance report. Let's run it, and let's wait for the results. We're going to wait a little bit. All right, that is done. And look, I have an isolated .log stuff. I have an isolated .log new file. That is a performance report. That performance report is not human readable like that, okay? You cannot open it in any, like, I don't know, text editor or VI or whatever, okay? You cannot open it over there. You can open it by using the command node, and then you're using the flag --prof process, and then you're doing isolate, and you're getting the report. So that is the performance report, and I want to talk about, there's a lot to talk about, but I want to talk about two parts of that report. The first part is summary, all right? That is the summary part. In the summary, we can see that the entire operation took us about more than 4,000 CPU ticks, okay, when I'm using the synchronous API. And then I would go to bottom-up heavy profile. Okay, and then bottom-up heavy profile is the first part that you have to look at in order to find problems and in order to find bottlenecks. Okay, but if you're going to look at bottom-up heavy profile, you would see that 98% of the time was spent in a lot of crypto stuff. Okay, more than 4,000 CPU ticks. Okay, and that is massive. Now, I would like to remove that file and I want to run the asynchronous and generate a new performance report. Remember, more than 4,000 CPU ticks. Now I'm going to do node --prof async crypto.js. Great. And then I'm going to do node --prof process isolated. Now let's see what's going on. First of all, let's look at the summary. Remember that the operation took us more than 4,000 CPU ticks before? Now we have a total of 130 CPU ticks. That is a massive improvement. And another interesting thing that you can see in the bottom-up heavy profile is that there is no there is nothing that really pops to your eye. It looks like that everything is sort of divided, okay? That means that the worst problem has removed from the table. And that is a good sign. And that is why what happened here is when we're doing synchronous operations, my event loop is working really, really hard on doing them instead of putting them in the worker thread pool. So because of that, whenever you have an asynchronous API, always use it. Now, okay, let's talk a little bit about the V8 engine and what is a JIT compiler. Okay, so V8 is a JavaScript engine that was developed in order to, for Google Chrome, and it was for running JavaScript very, very fast, and it is used for Couchbase, for MongoDB, and for Node.js. That is the most updated architecture of V8. The architecture is changing from time to time, but this is like the most updated version of it. So the JavaScript source code is being parsed. Okay, the result of that parser is an AST, abstract syntax tree, and that abstract syntax tree is arriving to an interpreter called Ignition. Okay, the Ignition interpreter is starting to run the AST, and there is a detection of hot code. What is hot code? Hot code is a code which repeats a lot of time. That hot code is being sent into Turbofan Compiler, okay, and that compiler is generating a more optimized version of that code, of the hot code itself. Now I want to talk a little bit about just-in-time compilation. So I just want you to know that JIT compiler or just-in-time compilation is something which exists in a lot of languages. Okay, it's like let's say it's a method of compilation. Okay, it's just saying that when I have an interpreter, okay, I am compiling things in runtime. That is the just-in-time compilation. I'm compiling hot code, and that hot code, I would use it. I would use the compiled version of that hot code when I will detect it again. JIT compiler is also appearing in Java. Okay, so whoever of you worked with Java, so Java source code are being compiled into bytecode. But the JVM itself uses JIT compiler, and when it detects hot code, which is pieces of code that are happening, that are duplicated a lot of times and used a lot of times, it is operating a JIT compiler on them, which creates on the fly in the first run a compiled version, put it in a cache, and fetch it every time that this is running. Okay, so what's happening in V8? Something very similar. We have a source code. We're tracing the source code. And when that tracing is detecting hot code, okay, when that tracing is detecting hot code, well, it sends it to the JIT compiler, which is Turbofan Compiler, okay, and creates a version of optimized code. What is the Ignition interpreter? I just, go over it very fast. It is an interpreter for V8. It translated to bytecode and is responsible for cold code, not hot code. Cold code is stuff that are running once, okay, against the hot code. And the Turbofan compiler is the compiler that on the fly is used to create a more optimized version of that code. Now, let's talk a little bit about how to help Turbofan to optimize your code. So first of all, I want to say to you that Turbofan is only optimizing functions. Remember that your boss or your team leader is always shouting at you that don't do copy paste And then if you're doing copy-paste, you would have to fix the same bug in 10,000 places. So here, if you don't do copy-paste, you get another advantages, which is that the Turbofan compiler would work. Okay? It's not working on a code which is not wrapped in functions. It's working only on functions. Okay? So that is the first point that I want to, that I want you to remember. The second point that I want you to remember is the amount of, the number of input types that you have, like the type variations. Okay, let's say that I have a function that receives 5 variables, okay, 5 parameters, I'm sorry, 5 parameters. And each of those 5 parameters is an integer. Okay, so that is a good situation. That is something which is called monomorphic function. Okay, but if, let's say, this function receives 5 parameters, and one of them is a string, one of them is an integer, one of them is a date, one of them is an object, and the fifth one is, I don't know, just pick something up, then that is a megamorphic function. And this is something that the compiler, the Turbofan compiler, would optimize. It would not do a very good optimization on that. Okay, so keep your function monomorphic as much as you can. Okay, so a little bit of definitions. Monomorphic is like one input type, meaning 5 parameters, all of them are date or all of them are integer. Polymorphic, it's like 2 or more input types, 2 to 4, I'm sorry. And megamorphic, it's more than 5. Okay? Now, the next thing that I want to say to you is please write idiomatic code, meaning a code that you can understand easily, a code which explains itself. I'm sure that if you're going to write that code, okay, then that rule would enforce itself, because if you can easily understand your code, well, you won't usually get functions with 7 parameters. Okay? Only in really edge cases. But if your code would be self-explainable, then I believe that most of your code would be polymorphic at the worst case. Now, okay, I want to talk about something which is called optimization and de-optimization. And for that, I would like to show you another quick demo. And for that, I would just open it. Okay. Okay. My question to you is, everyone in this hall can see the code clearly? Okay, cool. So I have an array here, and I think it has 10 million spaces. And I'm creating here a heterogeneous array and a homogeneous array. Okay? What would happen here? I'm going over this array in a loop. Okay, and when the index is 100, I'm going to push an object. Okay? On all the other places in the array, I'm going to push an integer. Now I have here a homogeneous array, and I am running on this array in a loop. Okay, and I will put integers in the entire array. Now I would like to run that code, and I'm taking time. It's just a small demo, so let's do node index insertions. Remember, the first one is heterogeneous. The second one is just integers all the way. First one, in index 100, we have an object. Okay, I want you to look at the time differences. In the first array, we have something which is close to 900 milliseconds. You see that? Second array, we have 12 milliseconds. Why that happened? And that's a massive difference. So why that happened? That happened because the JIT compiler is doing assumptions. Okay, that code is started to run. Okay, and there is an assumption here that oh, by the way, the JIT compiler also works on objects. So although it's not wrapped in a function, it would work. But there is an assumption here when index number 1 is a number or an integer, and index number 2 is an integer, and number 3 is an integer. So the compiler just assuming that all the way it's going to be integers. But then I'm breaking the assumption. Okay? On index number 100, I'm breaking the assumption. I'm saying, hey, here's an object. At the moment that I broke the assumption, I'm doing something which is called de-optimization. Okay? De-optimizations, meaning breaking the assumption, and then the compiler don't know what to do, and that code would never be optimized. Okay? So after talking about that, let's go back to the presentation. So as I said, okay. So optimizations. When the compiler is optimizing something, it's making assumptions. Okay? And if all of the assumptions are fulfilled, this is being optimized and the compiled version is being created. If one of those assumptions are being break, then that process is called de-optimization. Okay? So when you're doing de-optimization, okay, so what I want to tell you, never to do de-optimization, because when you're doing de-optimization, your code won't be optimized again, okay, and it can just cause like the massive time differences that you've seen in the demo. So de-optimizations is one of the worst things that you can do. Now, after we've spoke about that, let's go into the memory management. I hope that you're still like, unconscious because, it's kind of a heavy stuff. So stay strong. We're finishing soon. Okay, why do I need this? I just want you to know that when the garbage collector in Node is working, then your server would be frozen. Okay, the garbage collector is freezing the server. So it is good to understand what's going over there. And if your server is frozen and you don't have any synchronous operations, then the garbage collector could be like the next suspect. Okay, so let's talk a little bit about V8 memory management structure. So we have a code segment and there, the code is running. We have a stack. The stack is a data structure for local variables and pointers. We have a heap. In the heap, we have objects and closures. And the heap is divided to like a used heap and a free space. The stack itself, data structure, a very quick data structure to hold a specific like function pointer, the current function pointing. But what I want to say about the stack itself, that the garbage collection process starting from the stack, meaning that an object is considered active only if it has a pointer on the stack, okay? Or only if it's connected in the object graph to an object which is on the stack. And the heap is the data structure for complex object. Now, if you would look at this diagram, just like a small diagram of what allocated where. We have this function. It has an integer, a float, and an object. You see that the integer is on the stack itself. The float is a pointer on the stack to an object on the heap. And the object itself is also a pointer to the heap. And it is represented like this. Now the heap structure. So the heap is generational. Okay, so it's a generational object life system. And all the new objects are in the new space. and the old objects are in the old space. So the algorithm for garbage collection in the new space called Scavenge, and the algorithm for garbage collection in the old space called mark sweep. Okay, so I just want to say that an object, when it's allocated in the new space, it has to survive 2 scans of Scavenge, and when it's surviving 2 scans, it is going into the old space. Okay, and in the old space, the algorithm of mark sweep is trying to release it. So, just like a quick diagram to show you how the Scavenge scan is working. Here it's like a diagram of the new space itself, and the new space is divided into 2 parts, the to part and the from part. And the blue objects are the active objects, and the gray objects are the inactive objects. So the process is simple. Everything is going to from, and then only the active objects are going to space. Okay, and that is the process that's happening in the heap in the new space itself. As we said, if an object is surviving 2 of those scans, it's going into the old space, and when it would go into the old space, you would start having memory leaks. Okay? Now let's talk about the old space itself. Let's look at that code. What's tricky here, not really tricky, is that the D property would receive null. Okay, so the array that we've allocated to the D property would be like a released object. So that object ref, imagine that this is in the old space, so that object ref is represented like that. It's working in an algorithm that's called DFS. Whoever is not familiar with it, I really recommend to go to Wikipedia and see what is DFS exactly. Just to, you see that D is disconnected from this object graph. First, I'm starting from the root, which is A. I'm discovering all of its children. Here it has only 1 child. B, then I'm discovering all of B's children. I'm getting into C. And then I'm starting to mark all of them as visited from the bottom to the top. And at the beginning, I'm just going to erase all the disconnected objects. Now, the last thing, I hope that you're still like unconscious, but the last thing that we're going to do is find a little memory leak. So I would again open a code that I had prepared in advance. Okay. So this is a very simple code. Okay, so that code, every time that I'm hitting this server, this is a very, very simple HTTP server. So every time that I'm hitting this server, what would happen is that a listener would be registered, okay? And those listeners are not cleaned. I'll just show you like the, the basics in the beginning. So what you can do in order to start to detect memory leaks is work with Node Inspector. You work with Node Inspector with using the --inspect flag. I hope it is clear, but here I'm running my server with --inspect, hitting an enter, and then after doing that, I can just open my browser, and I am entering a URL which called chrome.inspect. Okay, I am pressing this link, and here I'm entering Chrome DevTools. Okay, I'm gonna take one snapshot, and here is the heap snapshot. Okay, and that is a snapshot of my memory, and it has lots of cool stuff. So now I'm going to hit my server several times. Okay, I prepared it in advance, and I will refresh it a little bit. And you remember that every time that I'm hitting my server, a lot of listeners are being registered. So, you know, it's a little bit more complicated than that because as you understand, we're just like going over like a little bit on the basics, but I'm going to take another snapshot right now. And I'm going to start looking at those two snapshots. First of all, what?
Can you zoom in?
How do I do that?
Command plus.
Okay, yay, working. Okay, so I would like to focus in one specific property here, which is array. And that is the size in the first snapshot when the server is up. And the size in the second snapshot is a little bit bigger. Okay, so I'm going to look at what I have here. But if I'm opening that, I can see that I have an object property that was not here before. And if I'm opening it, I am discovering all of my nice listeners that are here, and this is like a really huge collection. Okay, and if I would like hit the server some more times and would take another snapshot, then I would see the difference in that size here. It's a hard session. I really hope that all of you are alive. But we're done. And thank you very much for listening. Please follow me on Twitter. Everything would be uploaded in, I think, about 1 hour or 2 hours from now. And if somebody has any questions? No. Oh, hi. Yay.
Did you then say that using something like TypeScript would make you more likely to write optimizable code because you're fixing types?
I don't think so. I think that if your code is self-explainable, then you know, you would just get it out of the box. TypeScript helps in, to my opinion, in other stuff. It prevents you from writing a lot of defensive coding. It helps you like to understand what your functions returns. I don't know if it helps you. At least to me, it did not help to write like monomorphic functions. Any more questions? No? Okay. So thank you very much.